NENOMATICA, where mathematics meets YouTube excellence. Welcome to this video on intervals in the set of real numbers. Today, we'll learn about different types of intervals and how to represent them. Let's start with our first type of interval. If a and b are two real numbers, and a is less than b, we can define different types of intervals. First, let's look at what we call a closed interval from a to b. We denote this with the notation a, b, where the square brackets indicate that both a and b are included in the interval. This represents the set of all real numbers that are greater than or equal to a and less than or equal to b. Using set builder notation, we can write this as the set of all x such that x is an element of the real numbers and is less than or equal to x, and x is less than or equal to b. On a number line, we represent this interval with a line segment from a to b with solid dots at both a and b to indicate that they are included in the interval. Next, let's look at what we call a half-open interval from a to b. We denote this with the notation ab, where the square bracket at it indicates that it is included in the interval and the round parenthesis at b indicates that b is not included. This represents the set of all real numbers that are greater than or equal to a and less than b. Using set builder notation, we can write this as the set of all x such that x is an element of the real numbers and is less than or equal to x, and x is less than b. On a number line, we represent this interval with a line segment from a to b with a solid dot at a to indicate that it is included, and an open circle at b to indicate that it is not included. Now, let's look at another type of half-open interval from a to b. We denote this with the notation a, b, where the round parenthesis at it indicates that it is not included in the interval, and the square bracket at b indicates that b is included. This represents the set of all real numbers that are greater than a and less than or equal to b. Using set builder notation, we can write this as the set of all x such that x is an element of the real numbers and is less than x, and x is less than or equal to b. On a number line, we represent this interval with a line segment from a to b with an open circle at a to indicate that it is not included and a solid dot at b to indicate that it is included. Intervals are important mathematical objects that represent continuous sections of the real number line. Let's start by visualizing the real number line. This line represents all real numbers from negative infinity to positive infinity. We'll use this to show how different types of intervals appear on the number line. There are several ways to represent intervals using different notations. Let's explore each type. We'll look at open intervals, closed intervals, half-open intervals, and infinite intervals. First, let's look at the open interval, denoted as a comma b in parentheses. An open interval includes all real numbers x such that x is greater than a and less than b on the number line. We represent this with hollow dots at the endpoints a and b and a solid line connecting them. Next, we have the closed interval, denoted as a comma b in square brackets. A closed interval includes all real numbers x such that x is greater than or equal to a and less than or equal to b. On the number line, we represent this with solid dots at the endpoints a and b, indicating that the endpoints are included in the interval. Now, let's look at half-open intervals. First, we have a comma b in a square bracket and a parenthesis. This interval includes all real numbers x such that x is greater than or equal to a and less than b. On the number line, we represent this with a solid dot at endpoint a and a hollow dot at endpoint b. The other type of half-open interval is denoted as a comma b in a parenthesis and a square bracket. This interval includes all real numbers x such that x is greater than a and less than or equal to b. On the number line, we represent this with a hollow dot at endpoint a and a solid dot at endpoint b. Next, let's look at infinite intervals. The first type is denoted as a comma infinity in parentheses. This interval includes all real numbers x such that x is greater than a. On the number line, we represent this with a hollow dot at endpoint a and an arrow extending to the right toward infinity. Similarly, we have a comma infinity in a square bracket and a parenthesis. This interval includes all real numbers x such that x is greater than or equal to a. On the number line, we represent this with a solid dot at endpoint a and an arrow extending to the right toward infinity. Moving on, we have negative infinity comma b in parentheses. This interval includes all real numbers x such that x is less than b. On the number line, we represent this with an arrow extending from the left toward negative infinity and a hollow dot at endpoint b. Finally, we have negative infinity comma b in a parenthesis and a square bracket. This interval includes all real numbers x such that x is less than or equal to b. On the number line, we represent this with an arrow extending from the left toward negative infinity and a solid dot at endpoint b. The interval negative infinity to positive infinity, written as parenthesis negative infinity comma positive infinity parenthesis, represents the entire set of real numbers, denoted by the symbol r. This means all possible real numbers from negative infinity to positive infinity. Our next interval is 0 to positive infinity, written as bracket 0 comma positive infinity parenthesis. This represents all non-negative real numbers, denoted as our superscript greater than or equal to 0. This includes 0 and all positive real numbers. Now, let's look at negative infinity to 0, written as parenthesis negative infinity comma 0 parenthesis. This represents all negative real numbers, denoted as our superscript less than 0. This includes all real numbers less than 0, but not 0 itself. Let's continue with 0 to positive infinity, written as parenthesis 0 comma positive infinity parenthesis. This represents the set of positive real numbers, denoted as our superscript greater than 0. This includes all real numbers greater than 0, excluding 0 itself. Finally, let's examine negative infinity to 0, written as parenthesis negative infinity comma 0 bracket. This represents all non-positive real numbers, denoted as our superscript less than or equal to 0. This includes all real numbers less than or equal to 0, including 0 itself. Let's summarize what we've learned about these special intervals in the real number system. Now, let's understand the notation in detail. Round parentheses like these indicate that the endpoints are not included in the interval. Square brackets like these indicate that the endpoints are included in the interval. Let's also understand how to verbally describe these sets. Understanding interval notation is essential for many areas of mathematics, including calculus, analysis, and solving inequalities. Remember that parentheses exclude endpoints, while brackets include them, and specific superscripts on the r symbol help us quickly identify which subset of real numbers we're working with. Thank you for watching. In this video, we're going to solve a problem involving set operations. Specifically, we'll find the intersection of two sets. Let's first define our two sets. Set A is the open interval from -3 to +2, written as A equals open parenthesis -3 comma 2 close parenthesis. Set B is the union of two open intervals from -infinity to 1 and from 3 to +infinity, written as B equals open parenthesis -infinity comma 1 close parenthesis union open parenthesis 3 comma +infinity close parenthesis. To find the intersection of sets A and B, we need to identify all elements that belong to both sets simultaneously. The intersection is formally defined as A intersect B equals the set of all x such that x is in A and x is in B. Let's analyze this step by step. Set A consists of all real numbers from -3 to 2, not including the endpoints. Set B consists of all real numbers from -infinity up to 1, not including 1, and also all numbers from 3 onwards to +infinity. Now, let's identify where these sets overlap. Looking at our number line visualizations, we can see that set A and set B overlap from -3 to 1. Specifically, this corresponds to the open interval from -3 to 1, written as open parenthesis -3 comma 1 close parenthesis. In this video, we're going to solve a set theory problem where we need to find the intersection of a set A with the union of sets B and C. Let's get started. First, let's understand what these sets represent. Set A is the open interval from -2 to 3, which means all real numbers greater than -2 and less than 3. On a number line, it looks like this. Set B is the open interval from 1 to +infinity, which means all real numbers greater than 1. This is how it's represented on a number line. Set C is the open interval from -infinity to 2, which means all real numbers less than 2. On a number line, it looks like this. Now, to find A intersection B union C, we first need to find the union of sets B and C. The union of two sets contains all elements that belong to either set. If we look at our number line, the union of B and C covers all real numbers except for the points 1 and 2, which are the endpoints of our intervals. We can write the real numbers except for the points 1 and 2, which are the endpoints of our intervals. We can write this as B union C equals R minus the set containing 1 and 2, where R represents the set of all real numbers. Now we need to find the intersection of set A with B union C. The intersection of two sets contains all elements that belong to both sets. So we need to find the elements that are in both A and B union C. Set A is the interval from -2 to 3, and B union C is all real numbers except 1 and 2. Therefore, A intersection B union C is the interval from -2 to 3, excluding the points 1 and 2. Therefore, our final answer is A intersection B union C equals the open interval from -2 to 3, minus the set containing 1 and 2. To verify our answer, let's check by using set notation. We need to find the following: the union of the intervals -1, 3 closed and 2, positive infinity closed, and the intersection of the same two intervals. Before we solve this, let's make sure we understand the notation. The interval -1, 3 closed means all real numbers greater than -1 and less than or equal to 3. We use a parenthesis at -1 to show it's not included and a square bracket at 3 to show it is included. The interval 2, positive infinity closed means all real numbers greater than or equal to 2, going all the way to positive infinity. The square bracket at 2 means 2 is included. Now, let's find the union of these intervals. The union of two sets includes all elements that are in either set. When we take the union of -1, 3 closed and 2, positive infinity closed, we get all points that are in either interval. This gives us all numbers greater than -1, going all the way to positive infinity, which we write as -1, positive infinity. Notice that the union starts at -1, which is not included, and goes all the way to positive infinity. Next, let's find the intersection of these intervals. The intersection of two sets includes only elements that are in both sets. When we take the intersection of -1, 3 closed and 2, positive infinity closed, we get only the points that are common to both intervals. This gives us all numbers greater than or equal to 2 and less than or equal to 3, which we write as 2, 3 closed. Notice that the intersection starts at 2, which is included because it's in both intervals, and ends at 3, which is also included. Now, let's solve the second problem. We need to find the union of the intervals -2, 4 open and -1, 3 open. Let's understand these intervals. The interval -2, 4 open means all real numbers greater than or equal to -2 and less than 4. We use a square bracket at -2 to show it's included and a parenthesis at 4 to show it's not included. The interval -1, 3 open means all real numbers greater than -1 and less than 3. Both endpoints are not included, as indicated by the parentheses. Now, let's find the union of these intervals. When we take the union of -2, 4 open and -1, 3 open, we get all points that are in either interval. Notice that the interval -1, 3 open is completely contained within the interval -2, 4 open. This means that every element in -1, 3 open is also in -2, 4 open. Therefore, the union is simply -2, 4 open. In this case, the union doesn't extend beyond the larger interval because there's no element in the second interval that isn't already in the first. Let's summarize what we've learned. For the union of two intervals, we include all points that are in either interval. If one interval is completely contained within another, the union is simply the larger interval. For the intersection of two intervals, we include only points that are in both intervals. The intersection can be empty if the intervals don't overlap. Our final results are -1, 3 closed union 2, positive infinity closed equals -1, positive infinity. -1, 3 closed intersection 2, positive infinity closed equals 2, 3 closed. -2, 4 open union -1, 3 open equals -2, 4 open. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.